This is a generic review of topics and not a comprehensive list. Now, I would suggest that you start by printing out a periodic table of the elements, and then you can write all over it. So you can write things like electronegativity increases as you go from left to right, and increases as you go from bottom to top. You can also start writing the expected charges. So +1, +2, 2 minus, 1 minus. You can write the names of these columns as well, the alkaline earth, the transition metals, etc. Now, what I'm doing in the middle here with my transition metals is I'm writing the common ions for each of these. Like chromium makes more than one, so I have 2, 3, 4, 6. Iron makes a 2 and a 3. Copper makes a 1 and a 2. Cobalt, nickel, zinc, they all make a 2, as does cadmium and platinum. I'm also writing that lead and tin make 2 and 4. Aluminum is a +3. Students often forget that. Now, mercury has a special case. Mercury 1 exists as a diatomic ion, so it's Hg2+, and mercury 2 is Hg2+. Now, over here in this corner, I'm going to write all of my polyatomic ions. I'm going to start with ammonium and then write all of the rest of my ions down as well. One thing I did not do is I did not write any examples of naming or of chemical formulas. So there's plenty of space on this periodic table as well as on the back, even with all the things that I'm going to show you, to write some examples down as well. So the polyatomics that I have: ammonium acetate, cyanide, hydroxide, nitrate, nitrite, chlorate, chlorite, permanganate, bicarbonate, and carbonate. And phosphate. Phosphate is the only 3- that I have. So I did not use any of these to make any chemical compounds. Now, I prefer to color code. You need to find the color code that works for you. I didn't realize that the blue wasn't showing up. So here what I have done is I had indicated that the number on the periodic table is the number of protons. We have the letters, which mean the chemical symbol, and then the average mass is the mass that's given. Now, the average mass is found by the percent abundance of an isotope times its mass plus the percent abundance of a different isotope times its mass. Now, an isotope mass is found by adding the number of protons to the number of neutrons, and we have an isotopic symbol. So we use the chemical symbol, then we use the isotope mass in superscripted to the left, and then we write the number of protons subscripted to the left as well. So that's one way to show an isotope symbol. Then I'm going to define, so molar mass, you take the subscripts of the chemical formula, and you're going to multiply it by the atomic mass and add them together. So I'm going to provide an example here, just in case I forget during the test, and I'm going to use water. So 2 times 1.01 plus 1 times 16.00 is a molar mass of 18.02 grams per mole. So then I'm going to write in some of my electron configuration stuff. I have my D subshell, that's 5 orbitals, 10 electrons. Sometimes I forget things like that. This is my P, and then I have my P1, P2, P3, P4, P5, and that will help me to build an electron configuration very quickly. Now, these are not the whole electron configurations. What I'm doing is just writing down notes to help me remember how to get to my information quickly. So I'm going to write down a quick VSEPR chart, or VSEPR. So this is the valence shell electron repulsion theory geometry chart. And I'm going to start with the number of electron groups, just down in a column, 2, 3, 4, 5, 6. If I have 0 lone pairs, then I also have the electron geometry. So this is going to be linear, trigonal planar, tetrahedral. Then I will have a trigonal bipyramidal, and then I will have octahedral. Now, if I have 1 lone pair, I do not have 2 electron groups. So I'm going to write this in kind of a stair-step fashion. And so then I would have a bent, a trigonal pyramid. I would have a seesaw or a sawhorse, or I would have square pyramid, depending on how many electron groups I have. And then that continues. Now, of course, you would be welcome to write down examples of molecules that fit each of these geometries as well. And then I keep going until I get 4 pairs, and the 4 pairs is only for 6 electron groups. So if I have 4 lone pairs, then I only have two attached, it's linear. Now, the intermolecular forces that are at play, we have our dispersion forces. They're the weakest of the forces, and they're found in all types of molecules. However, we usually equate these to nonpolar molecules. Then we have our dipole-dipole, which is found in polar molecules, and we have our hydrogen bonding. Now, the hydrogen bonding is the strongest of the intermolecular forces that we look at, and it is a special case of hydrogen being bonded to N, O, or F. So a lot of times you will be asked, what is the strongest intermolecular force? You have to differentiate between these types of forces. Now, all single bonds are sigma bonds, and all pi bonds are found in our double and triple bonds. So when you have a double bond is comprised of a sigma and a pi. So when you have a pi bond, it automatically takes up a p orbital. So what's left hybridizes, and that becomes sp2. So you have an sp3 hybridized orbital if you have all single or lone pairs. You have an sp2 hybridized orbital if you have one pi bond, and you have an sp orbital if you have two pi bonds. Now you can have two pi bonds if you have two double bonds, or if you have one triple bond. So here I have some examples of my sp hybridized carbons with two pi bonds, just because that can get tricky. Now I'm going to move on to reactions. And this is where you might want to take some space to write down some example problems, because I did not go over any of the math in this review. So this is just to take care of a lot of the common questions. So an insoluble compound means that it forms a solid, and a precipitation reaction is 9 times out of 10 going to be a double displacement reaction, where you're going to have two aqueous solutions, and they will perform a double displacement reaction. That means the cations are going to switch places, and then you can find out if you have a solid. Now, the solubility rules should be provided for you, so you do not need to write them down here. Now, when you have a solid, that means it is insoluble, and you can form a net ionic equation. The net ionic equation is the ions that form the solid, liquid, or gas. If it's aqueous, there isn't a product to declare, basically. So an acid-base reaction will always form water and a salt. Now, the salt is formed from the cation of the base and the anion of the acid. And then we have our redox reactions. Redox is what I call it. Old habits die hard. These are our oxidation and reduction reactions. Again, 9 times out of 10, you're going to have something in its elemental state on one side of the equation, and then as an ion on the other side of the equation. So here I have copper as a solid as well as silver as a solid. Those are the elemental states, so the oxidation state is 0. But when they're in these compounds, they each have an oxidation state of 1. That means their ion charge is 1. So because on the reactant side, copper is a 0, but on the product side, it's a +1, we have a redox reaction. So then I'm going to move on to some thermochemistry stuff. Now again, it might be helpful to have an example problem written out, but I'm just going to write down the reminder things that I might need. So Q is going to be equal to your mass times C times delta T. The Q of the reaction is negative Q of the solution, where H, or the enthalpy, is going to be equal to Q divided by the moles of the solute. And in calorimetry, you have the Q of the reaction is equal to the negative Q of the water. You can parse this out and put it in pieces so that the Q of the water is mass times C times T, plus the Q of the calorimeter is C times T, if that helps you. However, I'm just writing down the reminder things. So now I have Boyle's law for gas laws, Boyle's law, Charles' law, and then the combined gas law, and then, of course, the ideal gas law with the R value. R is your constant. It is important to remember that T must be in Kelvin, and you need to watch the units. Also, you might want to write down the conversion. 760 torr, or millimeters of mercury, is 1 atmosphere. Now I'm just going to write down my solid cubic units. So when you have a simple cubic cell, you have 1 atom associated with it. A body-centered cubic is 2 atoms, and then this is face-centered cubic. That's going to be 4 atoms. Then we're going to have a phase chart. This was part of the homework, and if it's not in the lesson, I need to get it there. But you have energy and temperature, and I didn't draw this very well, but I want to go over what parts are what here. So each of your slopes, you have your working from the bottom to the top, you have solid, liquid, and gas. And then on your horizontals, that's where you have boiling and melting. So when we move from left to right, the point right before melting is the melting point, and the point right before boiling is called the boiling point. Now, when you have a gas going to a liquid, then you have condensation point, and then you have the freezing point. They are different. They are the same value, but they're in different places on the phase diagram.